So in this video, I want to give you practice setting up a reduction formula to allow you to calculate integrals of this form, definite integrals, and then to use it to calculate the integral I6, in other words, the integral from 0 to pi of cosine to the power of 6 of theta with respect to theta. So have a go with pen and paper, and then after you've attempted it, come back and you can see a detailed solution and some comments. Okay, welcome back. Let's look at the reduction formula on the next slide. So here is our class of integrals, and let's remember the integration by parts formula, and I've written it out here for a definite integral. And we're going to have to factorize this integrand in such a way that we can make our choices for the function that we're going to differentiate and the function that we're going to integrate. And clearly we can't integrate this immediately. If we could, we'd just do it without wasting time. So let's try to rewrite it. If we were to write 1, and then you'd have to integrate the 1 and differentiate this, you would end up with the integral of theta times some trigonometric functions. That would go outside of this class of integrals and would not help. Instead, what one can do is we can take out 1 power of the cosine. So we write this as the cosine times the cosine to the power of n minus 1. This we have to differentiate. After all, if we could integrate it, we would integrate this. This we can integrate as single power of the cosine. So what do we have? V prime, the derivative of v, is the cosine of theta. So its integral is the sine of theta. We can be confident about that by just checking if we differentiate it, do we get that? And yes, we do. The derivative of sine is cosine. What about the derivative of this? Well, we're going to have to use the chain rule. This means cosine of theta to the power of n minus 1. So we're going to bring down an n minus 1 factor. We're going to reduce the power of the cosine by 1. So we're going to have cosine to the n minus 2 of theta. And then from the chain rule, we multiply by the derivative of the function that was raised to the power. So we multiply by the derivative of cosine. The derivative of cosine is minus sine. So I'll put a minus sign here and write sine of theta here. And that is our derivative of this. So now we have all of the ingredients ready to calculate our integral. This is our integral. I'm just going to write in, and u times v is cos to the n minus 1 of theta times sine of theta. I've written that here. That's going to be evaluated between 0 and pi. Those are our limits. And we know that the sine of theta is 0 when theta is 0, when theta is pi, 2 pi, etc. So this is going to vanish. What about the second term? Well, we have a minus sign here, and then we integrate from 0 to pi, and it's this product, u prime times v. There's a minus sign there. Minus times minus means this is going to become positive. The n minus 1 factor does not depend on theta. I pull it outside of the integral. And then we have the integral from 0 to pi of cosine to the n minus 2 of theta. And then there's a sine here and a sine here. So overall we have sine squared. This looks for a second as though we're leaving the class. But then we think, sine squared is 1 minus cos squared theta. So what we recognize is that this integral can be written as a difference of two integrals in the class. It is the integral of cos to the n minus 2 of theta minus the integral, and now when you multiply that by cos squared, you get cos to the n. So it's the integral overall of cos to the n minus 2 minus the integral of cos to the n. We now just rewrite those using this notation. So going back to our equation, in is equal to, this is gone, we have n minus 1, remember it's positive. The first term in this difference is in minus 2, it's that times 1. And the second is this integral minus in. In is our original integral, so we take it over to this side. So to do that, we just, because of the minus sign, we're adding n minus 1 times in to both sides. We already had one of them here, and now we add plus n minus 1 of in's. And again, you see here that the 1 and the minus 1 cancel, so we are left with n times in. And that's equal to, on this side, n minus 1 times in minus 2. We've taken that already over here. So now we just divide both sides by n, and we have our result that in, the integral from 0 to pi of cosine to the power of n of theta with respect to theta, is n minus 1 divided by n times the integral with a lower power cos to the n minus 2. Again, as so often with trigonometric reduction formulae, you see you're going 2 steps down the ladder every time. This factor here is less than 1, and on the next slide I'll explain why that's the case by looking at a graph of the integrand. So what we did was we looked at this, wrote it as a member of a class, used the integration by parts formula for definite integrals, factorized the integrand in a way that one term could be integrated with the hope that we'd stay in the class, and we were able to do that by using this identity. And then it's just a matter of rearranging this algebra to find what in is in terms of in minus 2. Okay, let's use this on the next slide to calculate I6. So, on the previous slide, we obtained this reduction formula for our class of integrals. And to understand why we have this factor less than 1 here, I think it helps to sketch the integrand. So let's start off by sketching the cosine of theta. Now, the integral of the cosine of theta from 0 to pi is going to vanish. We have this area above the x-axis, this area, or theta axis, this area below the theta axis. They have equal areas, but this is below and contributes negatively to the integral and would cancel. And this is generally true. If you have any odd power of n, the integral from 0 to pi of cosine to an odd power with respect to theta will vanish. So we're only interested in even powers. So let's look at cosine squared. Cosine squared is always going to be positive. We've squared it. So if we look at the cosine, it starts here at 1 and it drops down to minus 1. So when we square the cosine to produce the blue curve, when the cosine is equal to 1, cosine squared is 1. When the cosine is minus 1, cosine squared is plus 1 again. And when the cosine vanishes here at pi over 2, the square is of course still 0. So it's going to go through this point, and this point. And the key thing to recognize is that in the middle here, cosine is a number that is between 1 and 0. And when you square it, you get a smaller number. So for example, a half squared is a quarter. So that means that the blue curve for cosine squared is going to lie below the cosine curve here. And then when we square it, we're going to get an identical curve here. And this carries on if you raise it to a higher power. If you look at, say, cosine to the 4th, that's the red curve here, then when the cosine is 1 or 0 or minus 1, you are going to get 1, 0, and plus 1 for cosine to the 4th. But cosine to the 4th is going to be smaller for all the other points than cosine squared was. So it's going to lie below it. So this tells us that the integral of cosine squared is going to be larger than the integral of cosine to the fourth. The integral for cosine to the fourth corresponds to the area between the red curve and the theta axis, whereas the integral for cosine squared corresponds to the area between the blue curve and the theta axis. And you can see immediately, if you were to think about, say, the integral of cosine to the sixth, the curve would start here, it would lie below the red axis, come to 0 here, lie below the red axis, and then come up to 1 here. So the integral of cosine to the sixth would be smaller again. And this explains why we have this factor, which is less than 1. Remember, you can write this factor, if you wished, as 1 minus 1 over n, so it's always less than 1. Okay, so now we have a little bit more of an understanding of why a factor like this is needed for this integral. So let's now calculate the integral I6. So we go back to this formula, n is equal to 6, so I6 is equal to 6 minus 1, 5 over 6 times I of 6 minus 2, I4. And now we write I4 again, using this formula with n is 4. So don't forget the 5/6 multiplying it. But now from this equation, we're going to get 4 minus 1, which is 3 over 4, 3/4, times I 4 minus 2, I2. And then we use the formula again. So 5/6 times 3/4 times, and now n is 2, 2 minus 1 is 1, over 2, so it's a factor of a half, times I naught, 2 minus 2. And I naught corresponds to the integral from naught to pi of cosine to the naught of theta with respect to theta, and cosine to the naught is just 1. So what we're going to get is an integral that corresponds to the straight line theta is equal to 1 from naught to pi, and that corresponds to the area of this rectangle here with height 1 and base pi, and that area is pi. You can calculate the integral as well, but we can understand it geometrically. So now we just have to tidy the numbers up, insert pi here. The 3 divided by the 6 is going to partly cancel, so that will cancel with that, leaving us with a factor of 2. So in the numerator, we are going to have 5 times pi, 5 pi. And in the denominator, we have a 2 from this cancellation, times a 4 times a 2, and that is 16. So that is our answer for this integral. So, on this slide, what we've done is we've used this reduction formula for our definite integral. We've used a bit of geometry to understand why this factor is less than 1. We could understand that quite nicely, I think. And then we can see how to just repeatedly use this until we reduce to an integral which we can calculate. Okay. On the next slide, if you'd like to practice this type of work, I'm going to give you a very similar exercise to calculate. So if you'd like to calculate a very similar exercise, why not swap cosine for sine? And I've changed the limits, and this is the result that you should obtain. So set up a reduction formula and then use it, and that's the answer that you should get. And with that, I'll stop this video.